Hey there, AP Stats kids. Two chapters left. Today we're going to be looking at chapter 11, 11.1 to be exact. Chi-square test for goodness of fit. If you took AP Bio with me or are currently taking AP Bio with me, this should be a lot of review. Okay. Also, shout out to the Twitch channel Live 2 Farm. That's the number 2. I was asked to do that this morning, and I promised I would. If you like watching some farmer sim, okay. So here's what we're going to be able to do. We're going to state appropriate hypotheses. We're going to check our conditions again. We're going to calculate degrees of freedom and p-values. We're going to do the actual chi-square test, and then we're going to conduct follow-up analysis. We aren't going to do the follow-up analysis. It's not an AP test. Sorry. I'm smart. Okay, so let's just start with an example. We will be doing this in class as well with some M&Ms. So they say the milk chocolate candy is produced in Hackettstown, New Jersey, has the ratio of this: 12.5% brown, 12.5 red, ... You guys can read. You're in AP statistics. Most of them are sad. They're blue. A quarter of them, though, show school spirit. So now Jerome's like, hey, I wonder if my M&Ms match up with what they say. And everyone's like, Jerome, you're so cool and popular for your math wisdom. So he counted his M&Ms and broke them into the colors. Because everyone knows brown M&Ms taste the best, right? That's according to my brother. And this is what he got. Now, if only there's some way to figure out whether or not that data is significant or not. I wish there was. So, if he was making a null hypothesis, he would assume that the candies matched up with the percentages given for Hackettstown, New Jersey. His alternative is they are not the same as Hackettstown, New Jersey. When you're chi-square testing for goodness of fit, you're either saying it is or it isn't. You can't say this is what the actual percentage is. No, it's either what they said or it's not what they said. Here's how I would have written that in symbols for my null hypothesis. I would say my null is at 0.125, 0.125. I'd put the percentages given in the original problem. And the alternative is at least 2 are incorrect. Well, if one's incorrect, there has to be another incorrect, right? Just based on how math works. But at least 2 have to be incorrect. All right? Don't state the alternative hypothesis that says, like, hey, the blue is wrong. No, you're just saying they don't match up. Okay? At least 2 don't match up. I think you should be able to say at least 1 more. How many candies of each color should Jerome... Sorry, I did sneeze. Should Jerome's class expect to find in their sample of 60 candies? So what's our expected value if we match up with Hackettstown, New Jersey? Well, you take how many total you had, and you multiply by the proportion that was said. We'd expect 7.5 brown. Now, 7.5 is not a legit, like, we're going to use that for calculations. I do understand. I guess you can have half an M&M, but that's not a reasonable thing. So we take total number of M&Ms times the proportion that is assumed, right? Or no. Oh, my neck needs to crack so bad. So that's how many we would expect to find if our bag matched up with Hackettstown, New Jersey. Are you guys keeping track how many times I say New Jersey? If you are, there's something wrong with you. All right, so, oh my gosh, I gotta sneeze again. Sorry guys. But anyways, this is the formula to find your expected values. N times P. Your number in your sample times the proportion that's assumed. It kind of makes sense, right? We did this earlier when we did proportions plugged in our calculator, right? Give you the percent. So, here's our observed, and here's our expected. And we made a cool bar graph. You can see sometimes they match up, sometimes they don't. But we want to know, is there a way I can quantify this? Or how likely is it to get our results by chance? Okay, right? That's always p-value. What's the chance of getting these results just by chance? Now let's draw a conclusion. And that statistic we're going to use to find this called chi-squared. That little symbol with the whee, the slide squared, chi-squared. Don't call it chi-squared either. Just chi-squared test. So let's figure out how to find chi-squared. Yay, math! It's your observed minus your expected squared over expected, and then you add them all up. Now, for this one, you can use your calculator. I honestly recommend you do these out longhand, because it's not so bad. It really isn't. It really isn't. I promise. So, for example, in our problem we were looking at with the M&Ms, there's so many M&Ms you got to lose yourself in the. We had 12 minus our expected value squared over our expected, right? If you took AP Bio, I teach you a way to use a chart for this, and this is the way I actually do it in real life. 3 minus our expected squared. If you please, I hope you have the data written down, okay? And then you add these all up, and that is your chi-squared statistic. Your observed minus your expected, square divide by expected. This is actually not too bad to do longhand. This one we get 9.8. That's our chi-squared value. Whee! Squared. All right, let's look at this. No, stop it. Ah. So, Carrie made a dice, and she wants to know if it's fair. So she rolled it 90 times and made a table how often each number showed up. So, what are we testing here? Our null hypothesis should be that every number is equally likely to show up. So, every number has a 1/6 or 0.166 chance of coming up. The alternative hypothesis is that they are not equally distributed. They're not equally likely to show up. So let's find the expected count for each one. So my expected roll, I would do 90 times 1/6. Okay? That's how I got these 15s. It's 90 times 1/6. Again. I took my n times p. So 90 times 1/6 is 15. And I did that for all of them. Right? Now to do chi-squared, I'm going to take each one, my observed minus my expected over my expected, plus my observed, cool color, minus your expected over expected squared, so on and so forth, right? And that's what they did. 12 minus 15 squared over 15. 28 minus, because you're kind of finding the square difference between each number and its expected value. Okay? So we got 14.4. That's my chi-squared statistic. Okay, 14.4 is my chi-squared statistic. Let's simulate 1,000 random samples of size 6. Actually, here I just want to show you. So chi-square is interesting because it's going to be skewed right. Okay. The larger chi-squared is, the more evidence there's going to be against your null hypothesis. You can do that for your p-value just like we did before. I want to get to the nitty-gritty. So you still have degrees of freedom in here. The higher the degrees of freedom go up, the more you can accept larger numbers. Okay, I'm not gonna, so degree of freedom of 1, chi-squared value of 8, you're going to probably reject your null. Degree of freedom 8 with a chi-square of 8, you might not. You're not going to. is what this basically means. As degrees of freedom goes up, the higher your chi-square statistic can be and still be, you're allowed a bigger number. Okay, because there's less skewedness. So if we had 6 colors for M&M candies, our degree of freedom would be 6 minus 1, which is 5. So if we looked at 9.8, we did chi-squared CDF, which is a thing, 9.8 to infinity, it would give us our p-value. We can also use a chart. The chart is fine for AP Bio because we just look at where accepts, reject, but now we want a p-value. This one's between 0.05 and 0.1, so I don't like that. I want a specific one, so this is the best way to do it. Chi-squared from 9.8 to 1,000, then your degrees of freedom was 5. Again, when you plug this in your calculator. No, stop it! So if you have your chi-square number, 9.8 to 1,000, and this is your degrees of freedom, right? DF. So you got 0.08, and that's the more specific way to do it. Failing to reject does not mean the null is true. It just means you can't disprove the null. All right? Last one, we're looking at that dice again. And earlier we found the chi-square was 14.1441, right? So now to find our p-value, all we do is we do x squared, or chi-squared CDF, lowers 14.41, our uppers 99999, degrees of freedom is 5, and we get a p-value of 0.0132. Okay? Which means we are going to reject the null. Are we good? Ask questions on this. I'm going fast, I know. My class is coming in soon. Make sure you check your conditions. All your expected counts should be at least 5. So random's the same, 10%'s the same. Large counts, so expected counts have to be at least 5. All your expected counts have to be at least 5. Everything else is the same. Last slide. Look at it. Love it. We already kind of talked about it. I don't want to. Ooh, we might do this one in class, actually, so hold off on it. Enjoy.